So we're going to do several questions this time, 21 through 25. So this is going to be section 8.3. Section 8.3 gets into what we call direct variation. So in this problem here, if 3 sweaters cost $43.41, how much would 6 sweaters cost? So this is an example of a direct variation question because if you notice this, the relationship with the number of sweaters and costs, if you buy more sweaters, so notice how if you increase the number of sweaters, your costs will also increase. So notice that when you increase either one of them, they go in the same direction. Similarly, if you don't buy very many sweaters, your cost is going to decrease as well. So notice how the units are going in the same direction. So when I have a problem like this, you may not need this. You can probably see, well, if there's 3 sweaters and now 6 sweaters, my cost should double. So I should be able to just say, hey, 43.41 doubled would be $86.82. That should be the answer. Now, if I want to use a proportion to solve this, notice how I have 3 sweaters and they cost $43.41. So notice how I went sweaters to costs. So I want to keep my units on the same side. So if you buy more sweaters, so we're going to buy 6 sweaters. The question is, how much would they cost? So this would be where our X is. So what I can do is set up a proportion just mirroring this right over here. So 3 over 6 equals this 43.41 over X. So remember, to solve a proportion, the shortcut becomes multiply the diagonal and then divide by the remaining number. So we end up dividing by the 3. So what I would do is multiply the 6 times the 43.41, and then I would divide that by the 3. And also it does give me that same answer of $86.82. So that would be the cost there, would be this $86.82. So direct variation basically means if one item increases, the other item has to increase as well. So they have to, the relationships have to be going in the same direction. So cost is one of these things that's usually a direct variation concept. If I look at question 22, this also comes from section 8.3. If it takes 50 ounces of grass seed to seed 4,000 square foot of line, at this rate, how much would be needed for a 9,600 square foot of line? So notice how, again, this is going to be direct variation because as you increase the square footage, you're going to have to increase how much seed you have as well. So this is going to be what we call direct variation. So notice how 50 ounces goes with this 4,000 square feet. So since I did ounces over here, I want to go the same direction, ounces to square feet. We don't know how many ounces we have, so that's going to be X ounces. But we do know that the square footage is this 9,600 square feet. So what I can do is use this method as a proportion. Don't change anything, just 50 over X. Just make it a proportion. And then 4,000 over 9,600. And we'll just let our calculator do the math. So we're going to multiply the diagonal to start with. So 50 times 9,600. Then we're going to divide that by 4,000. Oops. Let's just not do that just yet, though. I like to do that one at a time. So it looks correct. And then divide by 4,000. So it would be 120. So that also should make sense, 120 ounces, because if we double 50 ounces, that would bring that up to 8,000 square feet. So an estimation here, 100 ounces is going to get me close. So 120 sounds reasonable. So I'd be purchasing 120 ounces of grass seed would be my interpretation. So the next example is we have a machinist who's to make a metal plate represented in the figure to the right. what is the overall length of the actual plate? So what we have is a scale drawing. One side of the square is equal to 4.25 inches. I'm sorry, the side of one square is equal to 4.25 inches. So one square goes with 4.25 inches. So notice that in our problem, we have 1, 2, 3. So we want to know what the length or the base. So I would say they're looking for the bottom of this thing. How long is the base? So how many squares across is it going to be? So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Looks like it's 12 squares across. So if it's 12 squares across, what we should pick up on is the distance should increase as well. So if I increase the number of squares, my total distance should also increase. But we don't know what that actual dimension is. So if we double check that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 sides of squares. So that's going to be what we're looking for. So that's how we can set up a proportion here. 1 over 12 equals 4.25 over X inches, if you will. We don't know how many inches that actually is. So notice how I can cross multiply 12 times 4.25. And then divide that by 1, it's not going to do anything. So my answer should be 51 inches is the length of that base. So base usually applies to bottom of the plate. So I'm kind of thinking that's the bottom. So from here to there, how long is that? And it would be 12 squares long, or in other words, 51 inches. So got a couple more to look at here. So the number of kilograms of water in a human body varies directly as the mass of the body. An 87 kilogram person contains 58 kilograms of water. How many kilograms of water are in a 63 kilogram person? So what we can pick up on is if an 87 kilogram person goes with 58 kilograms of water, so I need to put person there. 87 kilogram person goes with 58 kilograms of water. Notice how they said varies directly. So I can just set this all up here. And 58 kilograms of water. So I need to do the person here. Again, the next question is, how many kilograms of water are in a 63 kilogram person? So the person is 63 kilograms, but we don't know how much water is in that person. So notice how we have 87 over 63 equals this 58 over X. So we have a proportion, and we could cross multiply to get that. There's also a formula we could have used that said, we won't use that because we don't have the constant there. So never mind, scratch that. So let's just go 63 times 58, that's the diagonal. And then if we divide by 87, we get 42. So 42 kilograms of water. So that should make sense because our weight of a person decreased. So that means our water should decrease. So again, that's that direct variation. If one decreases, the other has to decrease. If one increases, the other has to increase. That's kind of the pattern we picked up on that. So question 25, if y varies jointly with as x and z, find y when x equals 4, z equals 4, and the constant of variation is k equals 10. So we have this equation here where k is the constant of variation. So we have to just substitute into this problem. So y equals this 10 times then x is 4 and z is 4. So 4 times 4 would be 16. 10 times 16 would be then 160. So y would be 160. So they can give us a whole lot of meaning in that problem. So We just kind of just trust our little formula there for that one.